In this lecture, we're going to address the question of energy generation and transport in stars. The physics that describes how stars work is actually fairly well understood. It consists of a number of key parts. The first of these we've already met, hydrostatic equilibrium. This is the balance between pressure, which wants to make the star try to blow apart, and gravity, which wants to make the star collapse. It depends upon two relatively well-known pieces of physics: the law of gravity according to Newton, and the equation of state embodied by the ideal gas law. The pressure of a gas is dependent on the density times its temperature. We also need to have a source of energy. We've seen two of these sources of energy from the previous lecture: nuclear fusion, which is the principal energy source for the sun, and gravitational energy through the Kelvin-Helmholtz mechanism. Finally, a third piece of physics that we've not yet met is we need a way to transport the energy. We need to get energy from the inside, where it's generated, out to the surface, where it can shine away as the luminosity of the star. All of these pieces together are needed to be able to come up with a complete picture of the interior structure of a star. Let's look at these in detail. Hydrostatic equilibrium is the balance between the outward push of pressure and the inward pull of gravity. If pressure dominates, the star will expand. If gravity dominates, the star will contract and get smaller. A balance between these two, hydrostatic equilibrium, sets up a core envelope structure inside the star, in which you have a hot, compact core heated by the compression of all of the weight of all the gas above it, surrounded by a cooler, extended envelope that gets cooler as you move closer and closer to the surface, and the compression begins to leave off as you get less and less material above you. Stars, fundamentally, are big balls of gas that shine because they are hot. Stars are constantly radiating away internal energy by shining. The rate at which they lose energy is the luminosity, the number of joules per second leaving the surface of the star. To stay hot, stars need a source of energy to make up for the energy that they're losing due to shining. The available energy sources are nuclear fusion or gravitational contraction through the Kelvin-Helmholtz mechanism. Main sequence stars generate their energy by the nuclear fusion of 4 hydrogen nuclei into 1 helium in their core. There are 2 hydrogen fusion reactions that can occur in the cores of main sequence stars. The first of these we already met in the previous lecture discussing the lifetime of the sun. This is the proton-proton chain. This is an important nuclear fusion reaction that occurs at relatively low core temperatures, with temperatures less than about 17 million degrees Kelvin. It converts 4 protons into 1 helium nucleus with the release of energy through a 3-step process, a chain of nuclear reactions that occur in sequence. The second process that we've not yet met is called the CNO cycle. CNO stands for carbon, nitrogen, and oxygen. This turns out to be an important nuclear fusion reaction at very high core temperatures, temperatures exceeding 17 million degrees Kelvin. As you can see from the right, this is a 6-step nuclear reaction chain involving 4 protons and 1 nucleus of carbon. The proton-proton chain is the dominant nuclear fusion reaction that occurs at low temperatures inside of main sequence stars. It starts up and ignites at temperatures of the core reach around 10 million degrees Kelvin and will be the dominant source of fusion energy up to temperatures of about 17 million degrees Kelvin. It's the most important fusion source in the sun. When all is put together, it constitutes approximately 98.3% of the fusion that goes on inside the core of the sun. In this reaction, 4 hydrogen nuclei are fused into 1 helium nucleus, releasing energy in the form of gamma-ray photons, positrons or anti-electrons, which then head out into the star and very quickly find an electron and annihilate into 2 gamma rays, releasing more energy. And finally, the last bits of energy are put into the form of electron neutrinos that stream out of the sun, making its way across the universe and into our detectors. We can actually see these in large underground detectors like the Super Kamiokande Neutrino Observatory. This is the direct observational confirmation that nuclear fusion is responsible for the energy of the sun. The proton-proton chain is going to be one of the fundamental ways that hydrogen is fused into helium throughout stars in the universe, but it's not the only way. The carbon-nitrogen-oxygen cycle is the dominant hydrogen fusion reaction that comes into play when the core temperatures become very high. It starts up and ignites when the core temperature reaches about 15 million degrees Kelvin and will become the dominant fusion source when the core temperature exceeds about 17 million degrees Kelvin. In the carbon-nitrogen-oxygen, or CNO cycle, carbon acts as a catalyst to mediate the fusion of 4 hydrogen nuclei into a helium nucleus, with nitrogen and oxygen as intermediate products of the reaction. It's responsible for about 1.7% of the fusion that occurs inside the sun. If you remember from the previous slide, the proton-proton chain is responsible for 98.3% of the sun's energy, and so 98.3% proton-proton plus 1.7% carbon-nitrogen-oxygen fusion makes up 100% of the fusion energy going on in the sun's core. Both of these cycles share a common feature. They are responsible for taking 4 hydrogen nuclei and fusing them into one helium nucleus with the release of energy due to the mass difference between 4 protons and 1 helium nucleus, that 0.7% that is lost when you bind hydrogen into a helium nucleus. The difference with the carbon-nitrogen-oxygen cycle is the role of carbon. Carbon plays the role of a catalyst. We use the word catalyst in nuclear reactions the same way that chemists use the word catalyst. A catalyst is any component of a reaction chain, chemical or nuclear, that is not consumed by the reaction. In this case, the carbon, we're not going to go into this in detail, but the carbon enters the cycle where carbon fuses with 1 hydrogen, releasing a gamma ray and making an isotope of light nitrogen. The light nitrogen isotope is unstable. It decays into a positron and a neutrino, going into a heavy nucleus of carbon, carbon-13. A second proton fuses with the carbon-13, releasing a photon and making a nucleus of nitrogen-14, normal nitrogen, like the nitrogen we're breathing in this room. This nitrogen waits around for a while until it fuses with a third proton, releasing a gamma ray photon, and now making an isotope of light oxygen, oxygen-15, 1 fewer neutron than the familiar oxygen that we breathe in this room. This light oxygen is unstable. It emits a positron and a neutrino, turning into a heavy nitrogen, 15 nitrogen, which then in turn fuses with the 4th and final proton, which then splits into a helium nucleus and a carbon nucleus. You can see how the cycle returns back to carbon. Carbon enters the cycle at the top, 4 hydrogens fuse with various of the intermediate products, and at the end, 4 hydrogens have been fused into a helium, and the carbon comes back out. Because the carbon is not consumed by this reaction chain, we say that it acts as a catalyst. While this seems like a very complex nuclear reaction, it's often these nuclear reaction chains are what are important for energy generation in stars. The reason why nuclear reaction chains are required is because many of the fusion reactions important in stars require that, at least in the case of the hydrogen fusion into helium, 2 of these protons must be converted into neutrons. That's a very difficult reaction to occur, and so there's 2 pathways, either the pathway of the proton-proton chain or the pathway through the carbon-nitrogen-oxygen cycle. The end result is the same. 4 hydrogens are fused into a helium with the release of energy in the form of photons and neutrinos, which stream out of the sun and can be detected in large underground detectors. The rate at which nuclear fusion occurs is extremely sensitive to the temperature in the core of the star. Basically, the higher the temperature, the faster the nuclear reaction rate occurs. In some sense, this makes sense because You have to be having the nuclei move very fast to get close enough together for the nuclear fusion reactions to occur in the first place. The proton-proton chain depends upon temperature to the fourth power. If I double the temperature inside of the core of a star, the rate at which proton-proton fusion proceeds goes as 2 to the fourth power, or 16 times faster. The CNO cycle, on the other hand, is profoundly temperature sensitive. The CNO cycle fusion rate depends on temperature to the 18th power. If I double somehow the temperature in a core, the CNO cycle would run more than 262,000 times faster. This profound temperature sensitivity is an important reason why, as the temperature in the core increases beyond about 17 million degrees Kelvin, the CNO cycle quickly comes to dominate. Once it starts, the CNO cycle basically begins to take over in a very, very small range of temperature. However, this temperature sensitivity carries within it the seeds of what looks like a fundamental instability. Fusion releases energy, that photon in the form of photons. Those photons go into the gas, hit the gas, are absorbed, and heat the core. But as you heat the core up, you increase the rate of fusion. So more fusion makes the core hotter, but a hotter core makes the fusion run faster, which makes the core hotter, which makes the fusion run faster. And it sounds like a snowball running down a hill. It's an unstable positive feedback. This leads to a very important question. Why is it that this nuclear fusion doesn't run away and make the star explode like an enormous nuclear bomb? Why are stars stable and not exploding? The reason for this is that nuclear fusion inside of stellar cores is controlled by the hydrostatic thermostat. This hydrostatic equilibrium that sets up the core envelope structure also helps to stabilize the star against runaway thermonuclear reactions in its core. It works like this. If the fusion runs too fast, fusion makes a lot of energy. That energy is absorbed by the core, heating the core up. But if you heat the core because it's a perfect gas, you will increase the pressure in the core. This higher pressure, in turn, pushes against gravity and makes the core expand. As the core expands, the perfect gas law tells us it cools off, and as the temperature drops, the fusion reaction rate drops. Contrariwise, if the fusion somehow was running too slow, the core would begin to cool off. I wouldn't be generating energy fast enough to make up for the energy lost by the core. The lower core temperature lowers the core pressure. But if the core pressure is lower, gravity gets the upper hand and the core begins to contract. But as the core contracts, it begins to heat up, increasing the fusion rate. This leads to a compensating reaction. At core nuclear fusion, because it's going on deep in the center of a star in hydrostatic equilibrium, is stabilized by that hydrostatic equilibrium. It acts just like the thermostat in your house. You set the thermostat to a particular temperature, the furnace comes on, heating up the house. As the house heats up, if there was no thermostat in place, the house would just continually get hot until it'd be hot as a jungle inside the house. Your roommate might like that, but you know that costs an awful lot of gas and energy to keep the house that way. So you want to keep the house from getting too hot. So you have a thermostat. The thermostat senses when the temperature gets above a certain set point and turns the furnace off. The furnace now being off, the house will begin to cool off because of losses through the walls in the house, losses through the windows, and maybe your roommate's left a window open and cold air is getting in. The temperature slowly drops as energy is lost from the house until the temperature drops below the set point in the thermostat. At that point, the thermostat closes, turning the furnace back on and heating the house back up. If it heats up too fast, the thermostat opens and stops. If it cools off too fast, the thermostat closes and turns the heat back on. You get a stable feedback control loop going on within your house. The same thing happens inside of stars. hydrostatic equilibrium plus nuclear energy generation in the core sets up a stable hydrostatic thermostat inside of stars. This keeps the nuclear fusion from running away and making the star explode like a bomb. If we were to try to run nuclear fusion in the laboratory, nuclear fusion would proceed, creating energy. That energy would heat the gas. As it heats the gas, it would cause more fusion. But now in the laboratory, that fusion's occurring in a bottle or a vessel, not inside of a star, which is tamped down with all the mass of the gas. And if we let off fusion in the lab, well, we get a fusion bomb. So this is a way that stars are able to self-stabilize. Nuclear fusion inside of a core is self-regulating through the interplay between nuclear fusion and hydrostatic equilibrium.